August 12, 1945, Yokosuka Naval Arsenal, Kanagawa Prefecture, Japan. A group of Imperial Japanese Navy engineers gathered near a dismantled aircraft component under the hangar's high ceiling. The air was still. The floor showed oil stains, scattered rivets, and fragments of aluminum alloy. Nearby, a large crate marked U.S. Army Air Forces property stood half open. Inside it lay the upper turret assembly of a Boeing B-29 Superfortress. The turret's metal housing measured approximately 1.1 meters in diameter. Its twin .50 caliber Browning AN M2 machine guns extended forward, their barrels showing powder residue and slight heat distortion. A motorized ring mechanism connected the turret base to its rotating platform. Several optical sighting lenses and wiring looms were coiled beside it. The engineers wore khaki work uniforms with white gloves and carried calipers, notebooks, and drafting instruments. A single interpreter from the former Army Technical Bureau recorded English inscriptions stamped along the assembly. Markings indicated a General Electric Central Fire Control System, Type A1. One engineer noted serial number CFC 32467. Another technician began tracing circuit paths linking gyroscopic sensors to servomotors. The air carried the odor of lubricant and oxidized steel. To the left of the main table, a partially stripped tail turret rested on wooden supports. Its control gyros were exposed, revealing precision-balanced flywheels and miniature amplidynes. A disassembled gun sight lay nearby, its glass reticle etched with concentric range rings. A small generator labeled Bendix 24-volt alternator was placed alongside voltage regulators and relay units. A senior naval engineer named Lieutenant Commander Kubo directed the inspection. His notebook contained diagrams comparing the B-29's turret with that of the Mitsubishi G4M Betty bomber. 2 American maintenance manuals, recovered intact, were opened to schematic pages printed in English. Technical assistants recorded part weights in grams and cable diameters in millimeters. Outside the hangar, crated B-29 wreckage awaited cataloging. U.S. aerial raids had left several damaged examples across Kyushu and Honshu. Recovery teams transported components by truck for post-war study. The Yokosuka facility, previously used for naval ordnance testing, now functioned as a technical evaluation site under Allied observation. By mid-morning, the Japanese engineers completed initial photographic documentation. Each subassembly was placed on a grid-marked surface and photographed with a Type 89 plate camera. The resulting images were labeled by part number and orientation. Electrical continuity tests followed. Readings indicated minimal resistance loss across turret servo circuits, confirming the durability of American electrical insulation under high-altitude conditions. The engineers proceeded to dismantle the gunner's control module. Within the cast aluminum casing, they found precision-cut gears, gyroscopes, and differential resolvers. Every component bore serial marks, batch numbers, and inspection stamps. Notes recorded that no part appeared hand-fitted, tolerances were consistent and standardized. By late afternoon, the hangar's tables were lined with disassembled parts arranged by function, optical, electrical, hydraulic, and mechanical. The work progressed quietly, methodically, and without commentary. Each observation was entered into a numbered ledger. When the day's inspection concluded, the components were covered with muslin cloths and sealed under inventory tag number 87A. The team withdrew to prepare formal reports for the Naval Technical Department in Tokyo. The object before them represented the most complex defensive armament ever integrated into a bomber aircraft. Yet at this stage, the engineers recorded only measurements, serials, and diagrams, nothing more. The full significance of what they examined would emerge gradually in the days that followed. By 1944, the Boeing B-29 Superfortress had become the cornerstone of American strategic bombing. Designed under the United States Army Air Force's Very Heavy Bomber program, it incorporated pressurization, long-range navigation, and centralized fire control. Production occurred under strict standardization at Boeing, Bell, and Martin plants across the United States. Each B-29 carried 5 remotely operated turrets and 1 tail installation. The fire control system, manufactured primarily by General Electric, used gyro-stabilized sights connected through analog computers to servomotors on each gun turret. A central gunner, located in a pressurized compartment, could control any turret through an electric relay network. This allowed simultaneous defense without direct manual handling of the guns. Japanese aircraft engineers first received reports of this system in early 1945, following the capture of damaged B-29 units on Kyushu. Intelligence summaries describe mechanical sighting automation that corrected for lead angle and target motion. Prior to this, Imperial aircraft relied on manually aimed turrets using optical sights such as the Type 89 or Type 1 systems. These lacked stabilization and mechanical computation. The introduction of the B-29's remote control system represented a technological convergence between gunnery, computation, and electromechanical control. Its operational effectiveness became evident during raids on Iwata, Nagoya, and Tokyo, where bomber formations maintained heavy defensive fire from multiple synchronized turrets. Japanese night fighters recorded consistent difficulty closing within firing range. The Navy Air Technical Arsenal at Yokosuka, alongside the Army Air Technical Research Institute at Tachikawa, began collecting and evaluating captured B-29 equipment for analysis. Priority was given to the Central Fire Control (CFC) system, the AILA-1 model. Reports described it as combining gyroscopes, amplidynes, servo drives, and lead computing devices based on angular rate input. Between June and August 1945, the Japanese technical bureaus assembled documentation translated from captured American manuals. These included General Electric specifications, Bendix electric drive diagrams, and SPE gyroscope data sheets. Laboratory translation teams produced detailed Japanese language technical digests. Each document was stamped with Giken number 207, urgent analysis. The Navy's intent was not replication but comprehension. Engineers sought to determine manufacturing feasibility under Japan's wartime resource limitations. Tests indicated that such a system required copper, precision bearings, and electronic vacuum tubes of consistent quality, all of which were scarce by late 1945. In parallel, German reports from earlier technical exchanges were reviewed. Luftwaffe documents from 1944 referenced similar American fire control innovations and recognized them as decisive in air defense integration. These reports were now studied for correlation. By mid-August, the inspection at Yokosuka formed part of a coordinated post-surrender technical evaluation effort. Allied authorities permitted controlled examination of captured equipment for scientific study. The Japanese engineers, many from pre-war design bureaus such as Kugisho and Nakajima Hikoki, participated under supervision to document findings accurately. Within this context, the B-29 turret became more than a weapon. It represented a system architecture that merged mechanical precision with electronic computation, a combination not yet achieved in Japanese or German aircraft designs during the war. The dismantling sequence began with the upper forward turret assembly. Engineers removed the armored dome, revealing 2 solenoid-actuated elevation drives. Each drive rotated smoothly through a worm gear connected to a reversible DC motor. Tests with auxiliary power confirmed synchronized motion with minimal lag, measured at approximately 0.15 seconds response time. Inspection of the amplidyne units revealed compact rotary converters using carbon brushes and laminated armatures. When energized, these devices amplified control signals from the gunner's joystick into motor torque capable of moving the turret's mass at high speed. Technical notes compared their performance to Japanese variable resistance motor controls, which exhibited slower feedback and higher thermal load. Next, the optical computing gun sight was examined. Inside its housing, 2 rate gyros provided angular motion data. A differential gear system translated these signals into continuous correction for target deflection and aircraft movement. This allowed accurate lead calculation even when the bomber changed altitude or velocity. The optical alignment remained stable despite mechanical vibration. Measurements of internal tolerances revealed a precision level within 0.02 millimeters. Bearings were factory sealed with molybdenum grease. Wiring harnesses used color-coded insulation with printed circuit identifiers, standardized across all assemblies. The Japanese engineers noted that such uniformity indicated a mature industrial production chain with centralized quality control. Hydraulic recoil compensators were disassembled from the gun cradles. Each cylinder contained a metered valve allowing consistent damping during automatic fire. Recorded discharge pressures averaged 1,100 pounds per square inch. The mechanism reduced vibration and maintained targeting stability during continuous operation. Subsequent testing focused on the communication link between gunner's sight and turret servos. Oscillograph traces confirmed smooth signal transmission without distortion over the full cable length. Voltage drop across connectors measured less than 0.5 volts, indicating high-quality conductor material and precision crimping. The engineers also inspected the turret's armor and framing. The alloy composition, tested by portable spectrograph, indicated aluminum 24ST, modern 2024 T3, with magnesium and copper reinforcement. This material offered high tensile strength while maintaining low weight, approximately 2.8 grams per cubic centimeter. Such alloys were unavailable in Japan due to material shortages. One engineer tested the control box's synchronization function. When manually rotated, the turret followed precisely, returning to neutral alignment without overshoot. The response curve matched theoretical servo mechanism performance charts found in captured documentation. Detailed sketches were prepared showing gear ratios, shaft diameters, and electronic circuit layouts. These were compared to Japanese remote gun experiments from 1943, including the Mitsubishi Type 3 prototype, which lacked automatic lead correction and suffered from unstable feedback loops. The Yokosuka team produced 10 blueprint sheets summarizing their findings. These included circuit diagrams of the amplidyne control, exploded mechanical views of the turret base, and translated annotations. Each was archived under Navy Technical Report No. 1429, Study of U.S. Aircraft Automatic Fire Control Equipment. By the end of the analysis phase, the engineers had reconstructed a near-complete functional understanding of the B-29 turret's operation. What remained was an interpretation of its broader significance, how such machinery changed the scale and precision of aerial warfare. On August 20, 1945, the technical committee convened to summarize its findings. The meeting took place in a small administrative room beside the main hangar. Present were Lieutenant Commander Kubo, 2 electrical specialists from Kugisho, and representatives from the former Army Air Technical Research Institute. The compiled data demonstrated that the B-29's fire control network functioned as an integrated system rather than separate devices. Every gun position could be slaved to another via electrical relays, permitting a single operator to command multiple turrets. Angular rate data from gyros were shared across the network, maintaining consistent targeting accuracy. A written conclusion read aloud stated, "The system constitutes an electromechanical computing network for coordinated gun control. Operational integration has been achieved by means of closed-loop servo mechanisms and amplidyne signal multiplication." Subsequent tests confirmed this interpretation. When an optical gun sight was rotated through a set angle, all connected servos responded proportionally, maintaining identical azimuth displacement. The delay was negligible. Engineers calculated theoretical engagement efficiency. Using standard approach speeds of enemy fighters at 500 km per hour, the automated computation reduced manual correction time by approximately 0.7 seconds. That difference equated to several meters in firing accuracy. A separate memorandum documented the reliability results. After extended electrical cycling, no failure occurred within the primary control circuits. Brush wear in amplidynes remained within tolerance after 300 hours. By comparison, Japanese variable resistor controls required maintenance every 40 hours. It was also established that each turret possessed redundancy. Power for the servos could be transferred between circuits in the event of local damage. The network's modular structure allowed sustained function even after partial failure. During the discussion, one officer remarked, "It operates as if each gun were part of a single machine." The phrase was noted in the minutes. It reflected a factual recognition of systemic design rather than emotional comment. The committee concluded that the American approach had fused mechanical, electrical, and computational elements into a unified control philosophy. This represented a major step beyond prior concepts of independent weapon stations. Data sheets were forwarded to the Navy's Research Bureau for correlation with captured radar and navigation equipment. The analysis showed that similar servo principles govern both gunnery and autopilot systems. In quantitative terms, the B-29's remote turret system reduced crew exposure, improved firing stability, and simplified training. Its centralized design reduced manpower requirements per defensive gun by nearly 40% compared to earlier bombers such as the B-17. At this stage, the Yokosuka engineers formally acknowledged that the B-29 represented a machine-integrated aircraft. Every defensive, navigational, and control subsystem operated through electrical synchronization. It was not simply an airframe with weapons, it was a coordinated network of machines functioning under centralized computation. The realization marked a shift in technical understanding. The era of manually coordinated defense had concluded. Air combat was entering the phase of electromechanical integration, a fact now confirmed through direct observation and measurement. Comparative evaluation began immediately. Reports from the Army Air Technical Research Institute indicated that Japan's own remote turret projects remained at experimental levels by 1945. The most advanced, designated Type HOD-5 remote control trial, achieved only partial servo stabilization and suffered from inconsistent gyroscopic feedback. Production never exceeded prototype stage. German data, transmitted earlier through military liaison channels, described the Bf-110G Air Force rear turret experiment using Siemens electric drives. It achieved partial automation but lacked real-time computing adjustment. The American system, in contrast, achieved closed-loop correction and multi-station coordination. Statistical summaries prepared by the Yokosuka Bureau recorded the following: average B-29 sortie defensive engagement duration, 1.2 minutes per attack, mean rounds expended per confirmed kill, approximately 600. Comparable Japanese bomber data indicated 1,800 rounds per kill with manual control. These figures illustrated the operational efficiency derived from electromechanical computation. Industrial implications were also recorded. Each B-29 contained over 90 electric motors and 15 amplidyne units. Such production required extensive copper wiring, high-precision machining, and standardized quality inspection. By 1945, American war industry could maintain monthly output of over 150 units. Japan's maximum heavy bomber production remained under 15 per month. The fire control system's development lineage was traced to General Electric's 1941 research into power control amplifiers. Its adaptation to aerial gunnery followed successful trials at Wright Field in 1942. Subsequent production contracts involved Spey Gyroscope Company and Bendix Aviation for component supply. The Yokosuka report emphasized that such cooperation between private industry and the military enabled rapid development. In contrast, Japanese design bureaus functioned largely in isolation, constrained by limited material supply and dispersed industrial organization. A supplementary memorandum from the Naval Technical Department analyzed possible adaptation to domestic aircraft. It concluded that duplication was technically feasible but economically and materially impractical under wartime conditions. Copper shortages and limited vacuum tube output prevented mass implementation. Post-surrender Allied teams reviewed the Japanese reports. American technical officers confirmed the accuracy of most measurements and commended the thorough documentation. Portions of the Yokosuka findings were later incorporated into Allied intelligence summaries on Axis technical capabilities, filed under the Japanese Post-War Scientific Reports, Volume 3. The study established a broader conclusion: automation in fire control signaled the transition from manual operation to machine-coordinated warfare. It also demonstrated the logistical strength required to sustain such systems. By quantifying efficiency, reliability, and production scale, the analysis provided an objective record of technological asymmetry between wartime powers. The B-29 turret, though only one subsystem, illustrated the depth of American industrial organization and integration of science with combat equipment. In the months following Japan's surrender, Yokosuka's technical archives were transferred to Allied custody. The compiled reports on the B-29 Central Fire Control System were microfilmed and stored under the Tokyo Documentation Project. Copies were distributed to American and British Air Technical Intelligence units. Subsequent Western evaluations confirmed the precision of Japanese measurements. The amplidynes efficiency, at 85% power conversion, matched factory data from General Electric. Server response times recorded in Yokosuka matched American flight test results within a 5% margin. Post-war engineering studies cited the B-29 system as the first fully integrated analog fire control network in aviation history. Its principle of distributed automation directly influenced later bomber and fighter designs, including the B-47 and F-86. In Japan, surviving naval engineers from the Yokosuka team contributed to post-war industrial reconstruction. Their exposure to American systems informed later developments in servo control, precision machining, and electrical automation during the 1950s. Technical reports from that period reference lessons derived from foreign mechanical control studies, 1945. Archival correspondence between former Kugisho engineers noted that the B-29 inspection demonstrated the future direction of warfare, coordination of machines through computation. The tone remained factual. The observation was not philosophical but technical. Official U.S. Air Force records, declassified in 1951, credited the B-29's remote turret system with significantly reducing bomber losses during the Pacific Campaign. Defensive kill ratios improved steadily as crews mastered the centralized control technique. From a design perspective, the system represented the integration of three industrial disciplines: mechanical engineering, electrical amplification, and feedback computation. Its components, though individually conventional, formed a coordinated defensive mechanism unmatched by contemporary aircraft. By the end of 1945, both Allied and Japanese engineers recognized that warfare had entered an era governed by control theory and machine coordination. The turret inspection at Yokosuka became one of many technical evaluations confirming that the decisive factor in modern conflict lay not only in weapon power but in systems integration. In historical review, the event stood as a factual record of technological comparison rather than ideological contrast. No symbolic interpretation was attached. The report simply documented a superior mechanism and its implications for future engineering standards. Later industrial assessments traced Japan's post-war progress in automated machinery and electrical control to early exposure from such technical analyses. Servo-driven manufacturing tools, introduced in the 1950s, reflected direct continuation of knowledge first observed during the B-29 turret study. The official conclusion, as recorded in the 1946 Naval Technical Bureau summary, stated, "Examination of the American heavy bomber turret system confirms a complete mechanization of defensive fire control. It represents the culmination of coordinated design and industrial precision presently beyond domestic capacity." This statement, preserved without amendment, marked the factual closure of Japan's wartime technical evaluation. It also documented the precise moment when Imperial engineers realized that the B-29 Superfortress was not merely an aircraft of aluminum and engines, but, in the objective words of their own report, a flying fortress of machines.